Good afternoon, everybody, and thank you for coming to this lecture. It's the first time that I've ever followed Liz Bonin onto stage, so I'm not quite sure how this is going to go, but hopefully over the next 40 minutes or so, I'll be able to convey to you something about the story and the issues around microplastics. And in doing this, I want to take you back to a world that isn't that long ago. It's actually around the time I was born. So these two advertising posters on the left-hand side there are from an era around my birth in 1964. And you can see for the age of it, people were really excited about these fantastic new materials called plastics. Melmex, unbreakable plastic household products. And there's one from British Industrial Plastics about the excitement and the wonder of all these new plastic materials that had been mostly discovered, developed through the 1930s, but it was really in the period post-war, late 1950s into the 1960s, that this expansion of excitement around plastics happened. And if you read from this advertising poster, it says, "The wonder of plastics is in their versatility, their infinite possibilities. Types and grades are innumerable, each with its own properties, presenting a wide field of choice." So this is, it's an era of excitement, it's an era of discovery. Brilliant materials that can do incredible things. And in a really short time, like in 50 years, we've moved from there to a world where we have these fabulous looking high-performance, polymer composite, lightweight car bodies with, near kind of space-age futuristic appearance. These materials are brilliant, they're fantastic, they can do all kinds of things. But that is also their problem and also the downfall, because in that time, we've also become used to this crazy throwaway society where we think it's okay to mass produce enormous amounts of single-use disposable plastic. It's fabulous. It protects our food, it keeps moisture in, it keeps oxygen out, it does all kinds of amazing things to improve the delivery of our food in supermarkets. And it's really important to remember that plastic is not the problem. Plastic is a wonderful material that's been invented by incredibly clever scientists and technologists to manufacture it into all kinds of incredibly useful things. That is not the problem. The problem is us. It's our attitude to this material, the way we've come to think of it as an unimportant, cheap, disposable material that we can simply toss away over our shoulders and forget about it. The problem is, we now realise we can't forget about it because it's such a wonderful material that it's long-lived. It doesn't degrade in the environment, much of it, so it just carries on and on and on, and it stacks up in the environment, making bigger and bigger problems. Okay, so just to give you an idea of how this all looks, the global plastics production curve, you can see where it's going. It's an exponentially increasing curve. It's going ever upwards. We're now getting close to 400 million tons of plastic every single year produced. Okay, go back to when those advertising posters were, mid-1960s, you can see that was, like about 10, 20 million tons globally. Wasn't that much. Now, 400 million tonnes. And if you look at what it's used for, you'll see that getting on for half of it is used for mostly single-use plastic packaging. And that is quite shocking, and clearly it's leading to all kinds of issues. And we need to rethink, we need to recalibrate in order to figure out how we're going to deal with this particular problem. Because currently, of the 350 plus million tonnes of plastic we're making every year, estimates vary, but somewhere between 8 and 14 million tonnes of that is ending up in the oceans. And if we carry on, the projection is that by 2050, there'll be more plastic in the ocean than there is fish. Okay? And unfortunately, because it's such a new material, such a new problem, we really have no idea how long it's going to stay in the ocean. You can read all kinds of estimates for how long these materials survive in the environment, but we really don't know because we haven't done the experiments. It's only been around for 20, 30, 50 years. And certainly that isn't long enough to degrade much of this plastic completely away. So that summarises the kind of position we're in right now. And this Max Gustafsson cartoon kind of tells you all you need to know about the current problem. The problem with that is, if we go on, it's a reality. It's not just a cartoon. This is how many seabirds are nesting on cliffs around the world. So it just gives you some idea of what the result of this kind of situation has created. And if any of you were here earlier and watched Liz Bonin's documentary, Drowning in Plastic, you will have had some more visions of what that really means in reality for seabirds and all kinds of other animals. The problem of plastic waste is ever increasing. And if you look at this world map, it's a little out of date now. This is work that was published by Jambeck in 2015, but it gives you an idea about where the biggest problems arise. And the hotspot is in Southeast Asia. And you can see that most of the countries at the top of this list of the countries that create the most plastic waste going into the ocean, they're all in this Southeast Asian region. And I don't think it's very controversial to say that plastic litter is ugly. It's unsightly, it ruins environments, and it also harms wildlife. And of course, there are lots and lots of pictures all over the internet of animals, sea creatures that are affected very badly by this kind of pollution. But this, of course, this all relates to macroplastic. It's the stuff we can see, it's the big stuff. And that is quite easy to connect with and relate to because it's very, very visible. But what I want to tell you about in the rest of this talk is the other side of this story, the invisible side of this story, which is microplastics. And microplastics are defined simply as small bits of plastic. There are other kinds of definitions, but the easiest one is any small bit of plastic less than about 5 millimeters in size is considered to be a microplastic. 5 millimeters isn't actually that small, but the definition was cut at that size to make sure it includes some particular important small bits of plastic, which are the things called nurdles. And if any of you looked at the exhibition outside, we've got some examples of nurdles there. Nurdles are the primary plastic material. When virgin plastic is manufactured, it's usually granulated into these small pellets, which are normally called nurdles. And that's how it's shipped around the world to companies that then process it into whatever final objects we want. And these nurdles, they get distributed all over the world, they get spilt, they float around in the ocean, they end up on beaches. And that's why the microplastic size limit has been defined as 5 millimeters to make sure it includes those little pellets, because they're everywhere. Most of you have probably seen them on beaches. If you've been to the coast, you can find them. East Anglia, there's not so much actually, but if you go to the south coast of England, you will find that they're really quite common on beaches. And the problem with microplastics is they get everywhere. They're picked up by the wind, they find their way into watercourses where they go down river systems and eventually out into the oceans, and they accumulate. And it's quite a complex diagram. There's a lot going on here. But all you really need to take away from this is the fact that microplastics are everywhere. There is no place on the planet where the scientific community has been to search for microplastics where they haven't been found. They're present in the Arctic, they're present in the Antarctic, they're present in snow, in very clean places in the high Alps. They're present in the deepest areas of the world's oceans. So we're pretty sure by now that they've got everywhere. And I just want to spend a moment to just explain where all these microplastics come from. So there are two types of microplastics. The first type are called primary microplastics, and these are ones that are deliberately manufactured small because of their intended use or function. And this includes things like the small plastic particles that are put in exfoliants, in makeup, in toothpaste and so forth. Many of these have now been banned in the UK and in the EU, but many of the same companies that have had their products changed for the EU market, they're still selling these products full of plastic in other markets where they haven't been banned. There are lots of primary microplastics that are produced for paints and coatings. Epoxy powder coatings in lots of colours are shown there, but any tin of emulsion paint you buy to paint on your walls is absolutely full of tiny microplastic particles. There's also lots and lots of fibres that are produced for textiles to be woven into polyester, nylon fabrics, carpet, all sorts of things, and they're also present in lots of wet wipes and even in tea bags. And if you've looked outside, Electra has a lovely display of some of the work that she's been doing looking at hidden plastic inside tea bags. So these primary microplastic particles or fibres are in all kinds of products and environments. Okay, the other side of the microplastic story comes from the breakdown of larger macroplastic materials. And these are some photos I took on Southwell Beach a few years ago, and they all show bits of larger plastic in various states of degradation. You can see they're all discoloured, they're breaking up, and they're gradually fragmenting. And do you want to do another one? There's actually a video. I don't know if you go to the left-hand picture. Yeah, if you could just activate the video for a moment. When larger plastic objects find themselves in quite energetic environments, such as, this happens to be Lowestoft Beach, we've got some waves rolling in, so we've got this quite turbulent, energetic motion, coupled with this fantastic grinding medium called sand. And of course, this process, it kind of rolls and tumbles and damages plastics. And if you look on the bottom left picture, you can see some beautiful sort of smoothed, rounded pieces of hard plastic. They were actually taken in volcanic sand on a beach in Iceland. But what you should look at is not the lump of plastic you're seeing, but imagine that was originally some jagged piece of broken plastic from a fish box or something like that. And it's been tumbled and rolled in this sharp sand for a few months, maybe a few years, and it smoothed it all off into a nice rounded shape. Now think about all the plastic that you're not seeing, all the bits that have disappeared, going from the sharp, jagged, broken piece to this rounded lump that you see there. Where did all that go? All those tiny particles that have been worn off it by abrasion, they're all out there somewhere, in the ocean, mixed up with the sand, somewhere. And this is what contributes to this overall microplastic problem. Another very destructive element is sunlight, ultraviolet light, and you can see how this damages plastics that sit around in the environment. So the picture you see on the top right here is a fragment from a plastic children's stool, little stool about this size. It's out there on the table if you want to go and have a look at it later. And you can see, if you look at the surface of it, it was originally purple, but it's all gone sort of brown and bleached and crazed. And you can see that lots of little tiny bits of plastic are now peeling off it. It's just crumbling away because the ultraviolet light has damaged the polymer structure and weakened it to the point where it's degrading and falling apart. So that's how all these microplastics come about. And here's the maths bit. Okay? We just need to think about how, as particles break down and get smaller and smaller and smaller. So imagine you've got a cube of plastic, which is a centimetre cubed, and you cut it into 10 slices, each 1 millimetre wide, and then you cut it in each direction. You end up with 10 by 10 by 10, 1,000 cubes, each one's a millimetre. And then you take that millimetre cube and you cut it 10 by 10 by 10, and you get 1,000,000 cubes, and so on and so on. So if we do the calculation for a single 500 millilitre plastic water bottle, which has roughly 10 grams or so of plastic in it, you can do the calculation and you work your way down, and it turns out that one single plastic bottle can produce 10 billion cubes, each one of which is 10 microns in size. So that's about the size of a pollen grain. Okay, one bottle produced 10 billion microplastic particles of that size. And if I tell you now that we use about 13 billion plastic bottles annually in the UK, and of those, roughly 7.7 billion, so more than half of them, are plastic water bottles. How did we get to a situation where we think it's a good idea to use 7.7 billion bottles of water sold in single-use plastic bottles? But if you multiply 7.7 billion by 10 billion, that's annually how much small microplastic particles would theoretically be produced if all of those bottles broke down in the environment to that scale. Hopefully they won't, because of course if we had an effective recycling system, most of them would be captured, and the plastic in these, very high quality plastic, it can be melted down, recycled, reformed really quite easily. So there's no reason why all this stuff should be going into waste and into landfill. It's purely about management and process and our attitude to that material. And if that wasn't depressing enough, really sorry, that's just the plastic. Alongside the plastic comes a whole cocktail of dubious chemicals. Some of these chemicals are added to the plastic to give it particular properties, like phthalates are added to give a certain degree of flexibility to polymers, flame retardants are added, and so forth. So some of these components are deliberately put in the plastic to aid their structure, function, properties. And some of these chemicals are simply picked up by the plastic particles when they float around in the environment. Many of these molecules are quite hydrophobic. They just stick to the surface of the plastic. And they then get carried around in the environment with the microplastic particles, and then they can potentially be ingested by organisms. So each of these little plastic particles is potentially carrying with it a whole cocktail of chemical contaminants, some of which might be quite toxic. The honest truth is we don't really understand the implications of this. There are lots and lots of studies in the literature. Some of them say plastic particles carry all these toxins into organisms where they get delivered, and it causes all kinds of nasty problems. Some of this research says the plastic particles are so good at hanging on to all these chemical contaminants that they sequester them, they hold them, they protect the organism from the exposure it would otherwise have experienced if all these things were floating around free in the water. And we don't really know, in all honesty, where the balance is. Maybe it's different for different types of organisms, different types of plastics. It's an enormously complex question, but it's one that we need to think about and understand more. So this is the key question, I guess. Do they pose a risk? We have a lot of microplastic particles floating around all over the planet, in the water we drink, in the air we breathe, everywhere we go. But do they actually pose a risk? And the answer is, we don't know. We're kind of a bit concerned. We think they might pose a risk, but there isn't really a lot of very good evidence at the moment that they pose a significant risk, at least to humans. But we've only just started exploring this question, really. The first papers are starting to emerge. So quite recently, there was a study that demonstrated that plastic particles that we ingest can get into our blood. If they can get into our blood, they get carried all around our bodies. So where do they go? What do they do? Is that something we should be worrying about? We don't know. But maybe we should be worrying about it. We don't really, in some cases, know even how to start answering these questions, because to understand this whole science, to get a grip of what's going on, we need to ask lots of really apparently simple but actually quite difficult questions, like how many microplastics are there? How many are you exposed to every day in your daily life? Where are they? What are they made of? How are we interacting with them? Are they coming from fabrics? Are they coming from road dust? When do we encounter them? And is there some kind of critical level? that it needs to get to in your body, as a kind of whole body dose that's going to suddenly cause a really bad effect? And the answer is, we have no idea. And one of the reasons we don't know is because it's, strangely, really quite difficult to detect and measure microplastics. We need to have methods that allow us to quickly, easily analyze samples, find out how many microplastics are in those samples, and ideally also then figure out what kind of plastics they are, because that will give us a clue where those microplastics might be coming from. And this is really not an easy analytical task. If you get involved in trying to measure microplastics, you will inevitably end up using some quite high-level analytical equipment. And it's not that long ago, if you go back 20 years or so, there was very little research on microplastics, and most of it was very observational. People picking up nurdles on the beach, figuring out that there seemed to be quite a lot there, wondering where they came from, how they got there, why they'd been spilt, and so forth, and were they maybe causing problems. And in the early days, most of the work was done just based on visual observation, physical sorting of samples, picking out bits of microplastic that you could actually see, stuff that was big enough to pick up and handle. And they used techniques like hot needles. You can test a piece of plastic to see if it softens when you heat it up. If your small object softens, then it's probably plastic. If it doesn't soften, then maybe it's a sand grain or piece of mineral or something like that. So it's not a very sophisticated test, but it's quite a good test, actually, for determining if something's plastic. And that's fine if it's big enough to pick it up, to see it, to handle it, to put a needle into it. Fine, even if it's rather slow. But as research has evolved, we've moved more and more to large, very expensive, highly sophisticated instruments. And there's a couple of them shown here. There's a Hariba Raman microscope that should have arrived next week. If it wasn't for global supply chain problems, this would have been in our labs in the School of Chemistry next week. It is coming, but hasn't quite arrived yet. I'm assured it will be here in June. At the bottom, this is an infrared microscope, and we have one of these in the chemistry department. That's our kind of workhorse, our tool for trying to identify microplastics. The problem with these is they cost a lot of money. A Hariba Raman microscope costs £250,000. Okay, that's a lot of money to a university like East Anglia. It's an impossibly large, unimaginable amount of money to a lot of small labs in overseas countries, in developing countries, that maybe have the biggest plastic waste crises. The same with the infrared microscope. It's a little bit less expensive, maybe 120,000, something like that, but it's still an awful lot of money. And it's not just the instruments. You need people who understand how they work and are able to use them and operate them effectively to make those kinds of measurements. So this is really difficult issue. It's very obstructive to the kind of amount of measurement we need to do if we want to have some idea of how much microplastic is around in all different locations all around the world. So thinking about this, we realised that you really need a different way of doing business. You need to approach this question in a different kind of way to at least give you some first indications of where microplastics might be and how many might be present. So we needed to come up with some new methods, and this is an area where my group at UEA has done quite a lot of work, and in particular, we've developed a very simple, quite inexpensive, quite rapid technique that allows us to give a reasonable estimate of the number of microplastic particles that might be present in our sample. And this method is, oh, it's a bit dark, sorry, it's based on a technique involving sticking a fluorescent dye to the surface of the plastic particle. And it turns out that this dye, called Nile red, has this property of sticking to the surface of most types of plastics. It binds quite strongly, and when it sticks to the plastic, as you can hopefully see on some of these photos, it makes them fluoresce, it makes them glow, kind of orange and red and yellow colours when we illuminate them with a blue light. So if you shine a blue light on them, the plastic particles then appear as these sort of bright orange or red or yellow particles. And that allows us to see them in more complex samples against a dark background of lots of other particles that might be present. So we can spot all the bright fluorescent ones, count them, and in some cases pick them out and take them to one of those expensive instruments I just showed you to try and identify what kind of plastic they're actually made of. So a typical kind of sample process would look something like this. We get a sample from the environment. It might be soil, it might be marine sediment, it could be beach sand. If it's solids, we need to dry it, we need to do some separation steps. Often we need to digest other organic material that might be in the sample, which sometimes gets in the way of the detection process. And then finally, we filter it, and so it ends up on a filter disc in a funnel like this. And we add some of this Nile red dye, which binds to the surface of the plastic particles, and we can then take that filter membrane, place it in a simple imaging instrument, and measure how many of these bright fluorescent particles we have in our sample. Oh, sorry. And this just gives you an idea. It's quite an old slide, but it just gives you an idea of what you typically see from this kind of experiment. And you can see the image on the left is a composite of 24 high-resolution photographs. And you can see on this particular sample, we've got a number of really quite large, bright yellow fluorescent objects. But as you zoom in and look more closely, you can also see a lot of much smaller particles as well. So there's some small fibers, and using this method, you can go right down to particles that are 10 or 20 micrometers in size. So if you think back to the pollen grain slide, we can get down to about the same size as a typical pollen grain. And this allows us to quite rapidly image and count how many probable microplastic particles we have in this particular sample. It's not 100% reliable. Sometimes things that aren't plastic can also stain and appear bright and fluorescent. So there's some things that we might count that aren't plastic. There are also some bits of plastic that for various reasons don't absorb the dye. And so we miss them. But based on lots of work we've done, studies we've done, we're reasonably confident that it gives a decent estimate of roughly the amount of microplastic that's present in the sample. And this technique you can do really quite quickly. It's easy to learn. We've actually produced a training video, which is free to view on YouTube. You can go watch it tonight. Riveting viewing for those of you that don't do it. But, 15-minute video tutorial, and you have a reasonably good idea how to go about doing this kind of work. If you want to use an infrared microscope, please sign up for about a week, because you'll need to do some serious training to really get to grips with the intricacies of that kind of instrument. So this technique allows us to measure much larger numbers of samples than you could ever hope to measure using an infrared microscope. And it allows us to ask different kinds of questions. So we can start to think about maybe mapping a coastline to figure out if there are hotspots where there are much larger, or maybe some areas where there are no microplastics, and to start to understand the dynamics and the distribution of microplastics in environments. If you want to, if you need to, you can go on and you can pick individual bright fluorescent objects that you've identified and actually take them to an infrared microscope to ask the question, is this really plastic? And you can do this. I won't bore you with the details. It's quite tedious. But our experimentation suggests that probably around 70%, maybe 70 to 80% in some cases, of the bright fluorescent objects we detect, if we've taken appropriate precautions, are probably microplastics that we can identify the polymer type of, if we're lucky. And just to give you one small idea of what we can do with this, we can start to map areas. So this particular area is a study done in association with CFAS. They collected lots of samples from an area called Dogger Bank. It's a famous fishing ground off kind of northeast coast. And there we collected those samples. I didn't. Colleagues at CFAS went out on the ship and collected these samples. We got them back to the lab. We sliced them, we diced them, we processed them, we counted them, and we came to the conclusion that there are quite a few microplastics in these samples. Rough average, about 1,000 particles per kilogram of dry sediment. So every teaspoonful has 3 or 4 microplastic particles in it. Okay, if you multiply that by the total area of the North Sea, you get to an eye-wateringly large number. Of course, good scientists do not extrapolate. We're told this from the very first days of studying science. It is very dangerous to extrapolate. You shouldn't believe anything that is estimated from these wild extrapolations because it makes so many outrageous assumptions. But it is sometimes fun to do it anyway because it emphasizes the kinds of numbers that we could potentially be looking at. The North Sea is quite a small, enclosed area of sea. If you think about the whole of the world's oceans, think how much that could be. The numbers are quite eye-watering, and you rapidly blur as you read how many zeros are present in this number. Okay, just a very small comment about a kind of different direction of research that was also done using this Nile red staining technique. This particular research is, ironically, it's the piece of work that I'm most well known for, and I didn't even do it. But the work was done by an organization called Orb Media in association with a professor at New York Fredonia University. But my connection to it is that they used this Nile red staining technique that I talked about earlier to measure microplastics in a load of bottled mineral water from lots of different brands in different countries in the world. And what they concluded was that almost all of it contained microplastics. And the numbers are there. It's about 10 larger microplastics per litre and quite a lot of small ones, which we're not 100% sure whether they're microplastics or not, but quite a few of them probably are. This shocked a lot of people. Maybe it shocked you. It certainly made a lot of news. It rippled around the world over 24 hours. It led to a very interesting week in my life. And it led to the World Health Organization initiating a review of whether microplastics in drinking water posed a serious threat to humans. And in fact, that review was completed a year or so ago, 2 years ago maybe now, and their general conclusion was that in the greater scheme of global problems, microplastics in drinking water is probably quite a minor one. Given the number of people in developing countries that die from waterborne bacterial and viral diseases, microplastics are by a long way the least of their concerns. So this is a kind of, it's one of those worry problems in rich Western countries where we have the luxury of worrying. In most countries, many countries in the world, they have to worry about things like, is the arsenic in this drinking water killing me? Not, does it have a few microplastics in it? So it's important to get this in perspective, but it also emphasizes the prevalence of microplastics and the fact that it's something that's getting everywhere. How did these microplastics get in the bottles of mineral water? I'm not going to go into that now, but there's a whole discussion and debate one could have about that process and how they came to be there. Okay. So finally, what does that tell us about where we are? We know that microplastics are by now ubiquitous. You can't avoid them. They're everywhere. We're breathing them in. We're drinking them in our water. We're eating them in our food. Interestingly, there's a study that was done in Plymouth not that long ago, and they estimated, and this may well be a fairly high-end estimate, but they estimated that in the time it takes you to eat a leisurely plateful of food, something like 100 microplastics might have dropped out of the air onto that food as you consumed it. That's probably about 10 or 20 times the amount of microplastics that might have been present in the food originally. So if you were eating a plate of mussels, for instance, lots of work's been done on mussels. They filter feed, so they pick up lots of tiny plastic particles. So if you eat mussels, there's probably a few plastics in them because of the stuff they've picked up out of the environment. But compared with the amount of plastics that simply fell on your plate out of the air, the number in the mussels is probably a relatively small contribution. So that's food for thought, I think. And it kind of puts the whole thing in perspective. In a moment. So, are microplastics harmful? Back to what I said at the beginning, we really don't know. There's plenty of evidence that microplastics cause stress to various organisms up the food chain. Is this sufficient to change populations and ecosystems? We don't really know. We've got much better ecotoxicologists in the audience who can answer your questions afterwards. There's very limited data on larger organisms. So, as I said, the first data about humans and microplastics in humans is really just emerging from research at the moment. So, in a few years' time, we'll probably have a better idea. But right now, it's a very open question. So that's something you need to kind of keep an eye on. But I wouldn't lose too much sleep over it at the moment, because actually there's not a very great deal you can do to avoid microplastics. They're all around us, so you're going to have to learn to live with them. Okay, so what should we do? And this comes really back to what Liz Bonin said a while ago, if any of you were in her question and answer session. We need to take action. We need to do small things as individuals that may seem like tiny, futile gestures against a massive problem that we have no control over. But if everybody takes small steps and makes small adjustments to their lives, maybe we can gradually get on top of this problem. So, reduce, recycle, repurpose, try to minimize the amount of plastic that you're throwing away. Don't buy too many clothes. Go talk to Kate, if any of you did earlier in the day. Learn to repair, learn to repurpose, learn to do what our grandparents did. Make do and mend. Make it a fashion statement to not go out and buy loads of new clothes all the time. And the same kind of thing applies in your daily shopping. Avoid the water aisle. Why are we buying water in bottles in the UK? We have a very well-regulated water industry that delivers very high-quality certified water to us in our taps at virtually zero cost every day of the year. So why are we buying it in bottles? 7.7 billion bottles a year in the UK. So, avoid that kind of thing. Remember small things you can do. Just picking up a few bits of plastic on the beach when you walk or out in the countryside. Pick it up and put it in a bin. At least it's going to be contained somewhere where it may cause a little bit less damage. Of course, I want to do more research. I want to do more work to understand these problems better. So hopefully governments will understand that there's still lots of questions that need answering and will give us lots of money to help to try to answer those questions. But yeah, that's really what we can do. Try to be nice to the planet, reduce your footprint a little bit, tread a little bit more lightly, and that hopefully will make the situation a little better for everybody and for the next generation and for the generation after that. Okay, so I'd just like to finish by thanking lots of people. I'm not going to name them all because there's lots and lots of people, but people in my research group that have helped do lots of this research over the last decade or so. People from external collaborators that have helped to work together on really interesting, meaningful projects. So a couple of the CFAS people are in the audience, but I've also worked quite a lot with Anglian Water and with a whole range of other people. And of course, when you do research, you need money. And most of this money has come from various government sources, also a little bit from commercial companies. So I'd like to thank all of those people for helping to work with me on this really interesting journey to try to understand a little bit more about microplastics and why we need to understand them. So with that, I'd just like to finish and thank you for your attention.